What's up, everyone? Today we're going to be providing an introductory overview on hardware hacking, focusing on hacking UART. So let's dive right in and start by defining some important terms. UART stands for Universal Asynchronous Receiver Transmitter. Simply put, a UART device is a piece of hardware that performs data transmission between a CPU and peripheral devices. These devices are commonly used in microcontrollers and can be implemented in devices such as GPS units, modems, wireless communication, Bluetooth modules, and many more. Asynchronous implies that the device has no constant rate at which it reads data, or there is no clock. The communication itself is done via the UART packets, which are structured like so. There's one start bit, 5 to 8 bits of actual data, one parity bit, and 1 or 2 stop bits. The number of data bits transmitted is typically between 5 and 8, with 7 and 8 being the most common since an ASCII character is 7 bits for the standard set and 8 bits for the extended. Serial communication of ASCII characters is almost always least significant bit. The parity can be even, odd, mark, or space. The UART peripheral calculates the number of ones present in the transmission, and if the parity is configured to even and the number of ones is even, then the parity bit is set to 0. If the parity is configured to odd and the number of ones is odd, then the parity bit is also set to 0. Otherwise, it is set to 1 to make the count even or odd depending. Mark and space parity means that the parity bit will either be 1 or 0 respectively for every transmission. The number of stop bits determines how much of a break is required between concurrent transmissions and is most commonly configurable to either 1 or 2. Now let's move on to the fun part, actually hacking UART devices and other embedded devices. So in 2012, with the widespread adoption of devices like the Raspberry Pi and the Arduino, the hardware hacking scene experienced a huge explosion in popularity, often focusing on attacking the UART as the main vulnerability of these devices. Every electronic system consists of hardware circuitry. Similarly, embedded systems consist of hardware such as power supply kit, central processing unit, memory devices, timers, output circuits, serial communication ports, and system application-specific circuit components and circuits. Most of the time, these systems need some means to communicate to an external system or device, whether that be transferring data to an external device, sending and or receiving commands, or simply for debugging purposes. One of the most common means for a device to perform these communications is through UART. So if you're trying to hack an embedded device, say a router or an Amazon Echo, you first need to expose the UART ports. This is usually done with a good old-fashioned screwdriver, sometimes a hammer, and whatever else you need to crack open a device's protective shell. Once you've exposed the main circuit board, it's time to find the actual UART ports, which are usually located in a line of 3 or 4 pins and pads next to each other, though we've seen some devices with up to 8 pins and pads. At this point, it's time to determine which port does which function within UART. This can be done using logical analysis to figure out each port's function. If you're following along at home, you're going to want to get out your trusty multimeter right now. So there are 4 main functions that we want to figure out. We want to identify ground, VCC, TX, which is data out, and RX, which is data in. So let's start with the easiest port to identify, which is the ground port. First, you'll want to turn off your device, place your multimeter in continuity mode, place the black probe on any ground surface, which is any metallic surface on the board, and then place the red probe on each of the 4 pads, and when it beeps, you'll know that that's your ground port. Next, we're going to identify which port is VCC, which provides constant power supply. In order to do this, place the multimeter on DC voltage, place the black probe on ground, and use the red probe to check UART pins. Power cycle the device, so turn it off and turn it back on, and then the place where you see constant high voltages will be our VCC pin. Usually it'll be close to either 3.3 volts or 5 volts. Afterwards, we're going to want to identify TX, which is the data out port. And once you know VCC and ground, TX is the pin that has the biggest fluctuations in voltage during the initial 10 to 15 seconds of boot up. This is because a lot of information is typically transmitted from a device during boot up, so it makes sense that it would experience fluctuations in voltage as you turn on the device. And finally, identifying RX, the data in port, is easily determined by looking for the pin that has the lowest voltage during the entire process. Otherwise, it'll be the last pin remaining. There are also some devices, such as the Bus Pirate, which can automatically detect UART pin functions, allowing us to save time on this step. Once you've finished mapping which port does what function, now you're ready to solder in connections into the UART ports to communicate with your terminal. If soldering seems like too much of a commitment, the Bus Pirate allows you to create non-permanent connections with the device just by plugging in your device to the UART ports. The next step is identifying the baud rate at which the device sends data. Some common baud rates are standardized and used frequently in many devices, but theoretically it can be whatever the manufacturer wants. There are several options for figuring out the baud rate, from running your own baud rate script to experimenting using trial and error in a terminal program, or even acquiring some external tools, for example, the IKA logic tool, which is a tool that is designed to automatically find the baud rate at which a device runs. This process actually tends to require the most effort in the entire hacking process, but can be overcome with persistence and experimentation. At this point, you should be able to play around with the software of the embedded device now that you can read data coming out of the UART device and write in your own information. For some devices, this is enough to run a simple bin.sh and access the shell. Unfortunately, we didn't attempt this ourselves because we didn't have disposable electronics to experiment with. However, there are many videos online that demonstrate this process. So here's an example from YouTube showing how to gain root access on a router using this method. For this particular device, all he had to do was update the environment table to spawn a shell on boot up to gain root access. However, this process may differ depending on the particular device you're hacking. We actually found that this information is available online for most devices and can be found in hardware hacking community wikis and websites. However, depending on what device you're attacking, there could be more software obstacles in your way, such as plain text passwords, TLS certificates, unsecured private APIs, or whatever else. So at this point, it becomes a software issue and not the hardware hacking part. So why do we care about this vulnerability in the first place? Besides just playing around with your electronics and voiding your warranties, what are the bigger implications of hacking hardware? Well, it's hard to say since different embedded devices have such a wide range of functions, but when you're purchasing any hardware device, you're implicitly putting your trust into the product and the manufacturer. You're trusting the security of this device with your personal information, and it's scary to think that anyone with a hammer, a screwdriver, and this video can potentially set up a way to monitor the information you're putting in and getting out of that device. So sleep tight, folks, and be wary of Alexa. She could be communicating with an external third party, and you might never know.